We have now seen that electric flux depends on three things. It depends on the magnitude of the electric field. It depends on the area of the surface and the orientation of the electric field vector to that surface. With that said, we can take these relationships and describe them mathematically using the language of calculus. This leads us to a definition for electric flux. The electric flux d phi through a surface of area dA due to an electric field E is equal to the component of the electric field that is parallel to the surface area vector. I just threw out a bunch of words and variables, and right now, I don't think they have that much meaning. So let's sketch a picture. Let's say we'll just go back to our cube. We have a cube, and inside of a cube, there's a collection of charges, but we might not know what that collection of charges is. But what we do know is that we can measure the electric field coming out of the cube. And when we measure the electric field at various points, at some points we'll see that the electric field is going into the cube. At some points we'll see the electric field is leaving the cube. We'll see that in some areas the electric field is perpendicular to the cube, but there's some surfaces in which the electric field is going at an extreme angle with the surface of the cube. Let's label these field lines. Let's depict this with E for our electric field. Now, this cube is a collection of surfaces. This cube encloses a volume of space. Each surface has its own surface area. So let's define electric flux for a very, very, very tiny surface element. I'll represent that surface element here with a square. Now, this surface element has a certain area vector. That area vector is defined by the magnitude or the area scaling a normal vector. Let's look at this tiny bit of area on surface 2. This tiny bit of area, I'll signify it with dA sub 2. In order to define flux, we're going to need to know the orientation of the electric field with respect to a surface. And the way to describe that is through the surface's area vector. So if we have a tiny bit of area, then there's going to be a tiny little area vector. And that tiny little area vector is given as the product of a scalar value, which is the area, and a vector normal to surface 2. So we will label this vector n sub 2 for the vector normal to surface 2. This allows us to define the tiny bit of area on surface 2. Now, through that tiny bit of area is the electric field, which means we can define the electric flux through that tiny bit of area as being equal to the dot product that the electric field passing through that area with the area vector. Well, to generalize this, I don't need to subscript 2. So here we have an infinitesimally small amount of electric flux. If we want to know the total flux through this entire surface, then what we have to do is we have to start summing over an infinite number of these tiny little surface elements. So these tiny little surface elements, if we do it for surface 2, will give us the total flux through surface 2. So this tiny bit of electric flux, when we sum over an infinite number of tiny little fluxes or tiny little fluxes through these tiny little area vectors, when we sum all of those up, that allows us to create an integral over the area. Well, I'll use S to remind us that it's a surface. An integral over the surface of the dot product between the electric field and an infinitesimally small area vector. For this surface on this cube, then, there is a flux, an electric flux, given by the integral over that surface that we will call this integral the surface integral over that surface. And over surface 2, and in that spot, we might have a particular value of the electric field at that spot. Notice at that spot, the electric field is pointing out of the surface. But notice at another location, the electric field is pointing into the surface. It makes sense that the electric field remains inside the integral because the electric field may vary over that surface as we go from a tiny bit of area to the next tiny bit of area. For this, I'll just indicate that the electric field that we need to calculate the flux through surface 2, I'll just indicate that with a subscript 2, just to identify it on surface 2. We could then go to another surface and sum up. Let's say we do the electric flux for surface 1. Well, the electric flux for surface 1 would just be the surface integral of the electric field, which is just the dot product between the electric field and the area vectors on surface 1. So to do a representative area vector on surface 1, I'll just go ahead and sketch one. So here, right here, would be a tiny bit of area on surface 1. That tiny bit of area has a normal vector. That vector is normal to surface 1. Together, we get an area vector that is equal to the tiny bit of area on surface 1 and that vector normal to surface 1. And we can take that and dot it with the electric field. This would allow us to calculate the electric flux through surface 1. We could do the same thing for surface 2. Oh, and actually, let me label for surface 1, let me label just an electric field 1 to distinguish it from the electric field on surface 2 for surface 2. And I guess I need to relabel this upper surface. I called it area 2. I should have called it maybe area 3. If we look at this upper surface, let's label the electric field on the upper surface with E sub 3. Well then, if we wanted to calculate the flux through surface 3, we would just evaluate the surface integral of the electric field on surface 3. That would just be E3 dotted with a tiny bit of area vector. If I were to add that to surface 3, that tiny little bit of area, This right here would be the tiny bit of area on surface 3, and here is the vector normal to surface 3. Notice how on surface 3, the bit of electric field passing through that tiny bit of area is anti-parallel, or 180 degrees relative to the normal vector on surface 3. While on surface 1, the normal vector and the electric field passing through that surface element, they're parallel. So definitely the relationship between the electric fields and the area vectors matter. And that's why there is a dot product here. Remember, a dot product is defined as the product of the magnitudes of the vectors being multiplied using the dot product times the cosine of the angle between those two vectors. This is why it's important to keep track of the normal vector for that area, because if we could use this version of the dot product to calculate electric flux, where we might know the angle between the electric field and the area vector. If we continue to sum up all of the tiny little electric fluxes and all of the surfaces, we would end up coming up with a sum of all of those electric fluxes. That sum for the total electric flux through this surface would be given by the electric flux through surface 1 plus the electric flux through surface 2. We would sum up over all of our surfaces. And for this example, we have 6 surfaces that comprise this cube. So we would sum up the electric fluxes for all of the surfaces. And remember, the electric flux for each surface is given by the surface integral of the electric field, which is equal to the integral of the product of the magnitude of the electric field and the infinitesimal surface area differential times the cosine of the angle between them. It'll be important for us to be able to use either of these notations for calculating electric flux.